Hello and welcome. Welcome to the second lecture of Deep Learning course. And in today's lecture, we will cover the McCulloch-Pitts neuron. So let's start. Basically, in 1943, the two researchers named as McCulloch and Pitts have proposed a computational model of the neuron. They have developed this model, the McCulloch-Pitts neuron, because they were inspired from the biological neurons or from the human neurons or from the human brain neuron. Based on their motivation, they developed a model and they demonstrated that the artificially developed neurons, such as that they have developed, could simulate the simple logic gate operations such as the AND, OR, so on and so forth. The McCulloch was basically a neurologist and the Pitts was a logician, and the model that they have developed was made up from two functions, the g and f, where the first function g was performing aggregation on the received inputs, and the second function if then making the decision on the received aggregation, that is done by the first function g. And the inputs to their model were either excitatory, meaning 1, or it could be the inhibitory, meaning 0 or -1. And this is a graphical illustration of the McCulloch-Pitts neuron. Here, if you see the x1, x2, x3 up till xn, these are the input that is received by the McCulloch-Pitts neuron. And the values of these inputs could be either 0 or 1 or -1 or 1. Okay. The first function g receives these inputs and then did some aggregation on it. And the second function f then applies some thresholding logic and then makes some decision based on the received aggregation from the first function g. And the final decision could either be 0 or 1. So just remember these notations, the x1, x2, x3, these will be your input. The g is the function that is responsible for the aggregation, and the function f is responsible for the decision, and the decision is y. Okay. So now let's see it mathematically. If the function g, which is the first function that receives a set of inputs, if it receives a set of inputs such as x1, x2 up till xn, it computes the aggregation is summation of all the inputs, okay, starting from I is equal to 1 up till n. For example, if you have these inputs, the x1, x2 up till xn, your function g computes the aggregation in a way is x1 plus x2 plus x3 plus so on and so forth up till xn. Okay. And the final output, which is the y, could be described as to this aggregation, which is done by the first function, the g, then the function f is applied, and then you receive a final output. And you receive an output of 1 when the g of x, when the aggregation is greater than or equal to some theta, and otherwise you receive at 0 when it is less than a theta. And here a theta is a threshold parameter that we will see in today's lecture in more detail. Okay. For example, let's consider that you have set a threshold as 2, and your function, the first function g of x that performs the aggregation, it return you 3. Then you will check whether g of x is greater than or equal to theta. Yes, because 3 is greater than or equal to 2. Yes, then you will get a final output is 1, otherwise you will get a final output is 0. Okay, and the McCulloch-Pitts neuron can be used to solve simple binary functions such as the AND gate, OR gate, the NOR gate, and the NOT gates that we will see in today's lecture. Okay, now first of all, let's see how the McCulloch-Pitts neuron can be used to solve the AND gate problem. Okay, first let's try to understand the AND gate. AND gate is basically a gate. It is a logical gate that outputs 1 when all of the inputs are 1. For example, you consider that you have the AND gate that receives two inputs is x1 and x2 and the final output is y. So the truth table will become something like this: 0 1 0 1 0 0 1 1. The AND gate will give you output is 0 because here both the inputs x1 and x2 are 0, and here it will also give you 0. Here it will give you output is 0 because here one input is 0, but here when all the inputs, both the inputs, the x1 and x2, these are your inputs, this is your output. Here both of your inputs are 1, so you will get the output is 1 in the case of AND gate. Okay, so this is the truth table of the AND gate. The AND gate is implemented in the McCulloch-Pitts neuron by setting the threshold to the total of input variables. So in this case, you have the two input variables. So according to the McCulloch-Pitts neuron, you can implement the AND gate using the McCulloch-Pitts neuron by setting your threshold theta as number of input variables, which is 2 in this case. Let's see how we will implement this. If we have here x1, here we have the x2, here we have the function g, then we have the function f, where some threshold theta is applied, and then we are getting the output is y. So in this case, if we see here, you will get is 1 when your g of x will be greater than or equal to 2. So in this case, it will be 0 and 0. In this case, the sum is 0 plus 0, it is 0. So you will get output is 0 also. And here when you will add 0 plus 1, it is 1. 1 is less than 2. So you will get output is 0. Here in this case also 1 plus 0 it is 1 and 1 is less than 2. So you will get the output is 0 by the McCulloch-Pitts neuron also. But in this case when both the inputs are 1, so 1 plus 1 is equal to 2 and 2 is greater than or equal to 2, yes, 2 is equal to 2, so then you will get the output is 1. Okay. So if you have two inputs, then your threshold will be 2, and if your inputs are 3, then the threshold will be set to 3. And when all of the inputs have a value of 1, and whenever they will be aggregated, then it will reach to the threshold, and then the McCulloch-Pitts neuron model will be activated, and as a result you will get an output value of 1 at the output. And now let's see how the McCulloch-Pitts neuron can implement the OR gate. OR gate is basically a binary gate that returns 1 if any of the inputs are 1. The truth table of OR gate is something like this. If you consider the x1 and x2 is your inputs and y is your outputs, the truth table will become something like this: 0 1 0 1 0, 0, 1, 1. Here it will be 0 because both inputs are 0, and it returns 1 when any of the inputs are 1. So here it is 1 of the input is 1, so you will get here output 1, here you will also get output 1, here you will get output is 1. The OR gate in the McCulloch-Pitts neuron is implemented by setting the threshold to 1. So if you consider is McCulloch-Pitts neuron is x1, x2, when it is passed to the McCulloch-Pitts neuron, here is the function g, sorry, yeah, and then here is your function f where the theta is applied, and here we have set the theta is equal to 1. Then you are getting an output is y. So if you see this case, 0 plus 0 is equal to 0, okay, and 0 is less than theta threshold 1, so you will get the output is 0 by the McCulloch-Pitts neuron. And in this case, it is the 0 plus 1, 0 plus 1 is equal to 1, and 1 is equal to 1. It is equal to threshold, so you will get the output value is 1 by the McCulloch-Pitts neuron model. And similarly, in this case, the 1 plus 0, it is 1, and 1 is greater than or equal to 1, yes. So you will get the output by the proposed McCulloch-Pitts neuron also is 1. And in this case, the aggregation of two inputs 1 plus 1 of the two inputs x1 and x2 is 2, and 2 is greater than or equal to the threshold theta 1, yes. So thus you will get the output is 1. Okay. So when any of the McCulloch-Pitts model, okay, inputs are 1, in the case when you will be implementing the OR gate, then the McCulloch-Pitts neuron will be fired, such as in this case. Here it is activated when any of this inputs is 1, such as in this case this is 1, in this case this is 1, in this case both are 1. Okay, so this was about the OR gate implementation. Now let's see how to implement the NOR gate using the McCulloch-Pitts neuron. Basically, a NOR gate is a binary gate that outputs 1 when all inputs are 0. Otherwise, it returns you 0. So its table is looking something like this: x1, x2, and y. When it is 0, 1, 0, 1, it is 0, 0, 1, 1. When all inputs are 0, then it gives you 1, and otherwise it gives you 0. So in this case, here will be 1, here will be 0, 0, 0. So it is basically an opposite of the OR gate. And the NOR gate is implemented in the McCulloch-Pitts neuron by setting the threshold as 0. So if you remember previously here, we have set the threshold as g of x is greater than or equal to theta. But in this case, we will set the threshold as g of x is equal to theta, not greater, not less. So in this case, when all of the inputs to the McCulloch-Pitts neuron will be 0, then the aggregation result will be 0, and hence the McCulloch-Pitts neuron will be fired. So if we see the McCulloch-Pitts neuron as x1 and x2 that will coming to the aggregation function g, then the function f will be applied on it to make the final decision y, and here the theta is 0. So in this case, 0 plus 1 is equal to theta, yes. So then this hit will be fired here, and you will get 1, value 1. In this case, it is 0 plus 1, it is 1. 1 is greater than theta, it is not equal to theta, and our theta in this case it is 0. So thus you will receive an output is 0. In this case, 1 plus 0, it is 1, and our theta is, or threshold is 0. and this aggregation value, the g of x is not equal to theta, so thus we will get 0. And similarly in this case, the 1 plus 1 is equal to 2, and this value, the g of x, the aggregation value, which is 2 in this case, it is not equal to theta, which is 0. So as a result, we will get a value is 0 here also. So this is the way by which the NOR gate could be implemented using the McCulloch-Pitts neuron. Okay. Now let's see the NOT gate. The NOT gate is a Boolean logic gate that activates when the input value is 0, and it gives you a value is 1 when the input value is 0, and an output value is 0 when the input value is 1. So if we see the truth table, it is something like this. If we have the input is x, the output is y. When the input is 0, then we are getting 1. When the input is 1, then we are getting is 0. The NOT gate could be implemented using the McCulloch-Pitts model by setting the threshold value to 0. Okay, so we will set the threshold is theta is 0, and it is activated when the summation g of x, okay, is equal to theta, which is 0. So now if we see in this case, when the input is 0, its summation will be definitely 0. So it is equal to the threshold, so then it will activate it here. And in this case, it is the summation, the g of x value will be 1, and 1 is not equal to theta, which is 0. So thus it will give you an output of 0. Okay. And the NOT gate just allows one input, and when its value is 0, then it equals to the threshold, and thus it triggers the McCulloch-Pitts model. By the word triggering the McCulloch-Pitts model, it means that it will then fire, it will then activate, it will then give you the output of 1. So this was about the McCulloch-Pitts neuron, and in today's lecture we have explored that how the McCulloch-Pitts neuron can simulate the basic logic gates such as the AND gate, OR gate, so on and so forth. So in summary, if we see the gate and the threshold, while implementing these logic gates using the McCulloch-Pitts neuron model, okay, the threshold. For the AND gate, the threshold is the number of inputs. If you have 2 inputs to the AND gate, then your threshold will be 2. And if your inputs to the AND gate will be 3, then your threshold will be 3. And if your AND gate is receiving 4 inputs, then your threshold will be 4. And for the OR gate, it is equal to 1. The threshold could be greater than or equal to 1. And for the NOR gate, it is, let's say, theta, it is greater than 1, and in this case theta is, sorry, theta here it is equal to 0, and in the case of NOT gate it is also equal to 0. So this was all about today's lecture. I hope you will have enjoyed this lecture, and in the next lecture we will implement this logic practically in Python. Thank you so much. See you in the next lecture.